All right, let's do another one here. The following chart shows the position as a function of time for an object. You've heard that before. We did it yesterday. This time we have, let's see, starts off at x equals 5 meters, moves to 9 meters after 1 second. This looks kind of familiar. Okay, after 5 seconds it's at 25 meters, but then it starts going backwards. For the stretch from 5 seconds to 10 seconds, it's going backwards. So what's that graph going to look like? Well, to start off, I'd label the axes like I did before. T in seconds, have the origin down here. I can use the same horizontal scale I did, 5, 10. I can use the same vertical scale, although stuff is going to be just kind of scrunched in the bottom, but that's okay. We can live with that. Let's see, 25 meters. Whoops, I don't have to put labels on these because when you put the units at the top of the axis or at the end of the axis, it's understood that everything in there has those units. So this means 25 meters, this means 50 meters. Similar to a data table, if you put the units at the top, you don't have to put them in the cells. You can just have the numbers there. So start off by here, do the usual routine, and if you do that, you get a graph that looks like this. Whoops, no, not that graph. A graph that looks like this. Okay, it's doing something like that. And we could do as we did before, get the average velocity from 0 to 5 seconds. That would be this stretch in here. And if we did that, we'd have our V average equals delta x over delta t. x5 minus x sub 0, t5 minus t sub 0. Plug in the numbers here, and I get 4 meters per second. Now, when you write down an equation starting like this, you're writing the equation in what I call variable form. And you should do that on tests especially, because if on a test all I see is something like this, or worse yet, just the answer, I have no idea if you did it right. And what I'm grading you on homework and on your tests is on your solution. And if you have no solution, you got a right answer, you'll get 1 out of 5 or 1 out of 10, but that's not going to help you pass a test. So start off by writing the equation you're using in variable form. Keep units everywhere in your calculation and then do that. All right, so that was for 0 to 5 seconds. Now, just looking at this graph, we can see this thing's going backwards in this part of the thing from 5 to 10 seconds. Does that show up in the average velocity? Yes, it does. Plug in the numbers, delta x over delta t, x10 minus x6, t10 minus t6. 10 meters minus 22 meters, 10 seconds minus 6 seconds. 10 meters minus 22 meters, I did those in the correct order, is negative 12 meters divided by 4 seconds. That comes out to negative 3 meters per second. It's going downhill. The slope of, or the graph is going downhill. That's a negative velocity. And so we can see that. How do the two velocities compare? And could we tell that by looking at the graph? Well, it may be a little hard to know that the magnitude of those velocities, 4 meters per second here and minus 3 meters per second, that might be a little tough to see just by looking at the graph, except that in the first 5 seconds it goes from 5 meters to 25 meters, and in the next 5 seconds it goes from 25 meters down to 10 meters. So this is only a drop of 15 here. I think I went from 6 to 10 in this calculation, but this didn't fall as far as it rose in the first. So it's not surprising that the magnitude of this velocity is bigger than the magnitude of that one, but the big deal is the sign. Okay, can I tell just by looking at it that this would be a negative velocity? And yes, I can. It's going downhill. So you can learn things by looking at the graph. So that was that problem. We kind of raced through that, but that's okay. What about the next problem on the sheet? Shows a position versus time graph for an object. Okay, well, let's see. Holy cow. It goes from 5 meters up to 145 meters. Going to have to do something drastic with our vertical scale here. X in meters, T in seconds. I can still have the origin down here. The time is just 10 seconds again, so I can have a 5 here and a 10 there. That part's easy. But those meters end up being the position. I'm going to have to do something drastic. I want to stay with a linear scale. This time I'm going to let each little jump on here be 10 meters. And so this would be 50 meters. This would be 100 meters. And I can get all the way up to 130 here. And what I'll do is fudge a little bit. This would be 140. This could be 150. I'm sticking it there because I already wrote X in meters over here. And I can get that last point there at 10 seconds. It's going to be at about 145. So it's going to be way up here. And it starts off way down here. In between, it makes a pretty significant jump. So here's what that graph ends up looking like. And these are the data points. First thing it asks is average velocity from 0 to 5 seconds. Well, we do just what we did before, delta x over delta t, except this time our position at 5 seconds is 50 meters. So 50 meters minus 5 meters is 45. 5 seconds minus 0 seconds is 5 seconds. 45 meters divided by 5 seconds is 9 meters per second. It's got a much higher average velocity, and that's just in here. And I connected the dots here. What we calculated for that average velocity is the slope of the line connecting those two dots. That average velocity doesn't tell us anything about what's going on in between those 2 points, although we can see it here, some of it. But that's just what it happens to be. Then it has determined the average velocity from 3 seconds to 10 seconds. Well, go through the same thing again. x10 minus x3, t10 minus t3. Start off with the equation in variable form. And these are plugging in the numbers. End up with 17 meters per second. Almost twice as much. Well, that's the slope of a line connecting the 3-second position and the 10-second position. You connect those two data points and it's a much steeper line than this one happens to be. And you can tell that by looking at them. This kind of gives rise, the average velocity may not be the complete picture. For instance, let's suppose that we had a curve that, I need a one-sided piece of paper here. Good grief, what did I do? Oh well, let's do it on this one. Suppose you had a graph that did something like this. Okay, and you had data points for every one of these, or an awful lot of the positions in here. So you've got, every second or so you've got a data point. Well, what if you wanted to know the velocity at this point over here, the instantaneous velocity at that point? So here's the point we're interested in for some reason or other. And you do something like, well, let's pick 2 points that are equal side of that. or equal distances either side of that, and you get maybe this point and that point. So you use those and you'd be calculating the slope of this line. That doesn't look too good. Okay, well, pick points that are a little bit closer together. Pick this one and this one. Okay, yeah, we're still not getting anywhere near there. Right. What you'd have to do is start zeroing in on this thing, getting closer and closer from either side. And eventually you'd be doing something where you'd pick a point that's just a smidgen to the right of the point we're interested in and a smidgen to the left, and calculating the slope of the line connecting those 2 points. Now, you may not have done this in calculus yet. Some of you may have taken calculus, but what you're doing is I'm going to write instantaneous here, except we usually just call it v, the velocity. It's equal to the limit as delta t goes to 0, the thing on the horizontal axis goes to 0, of delta x over delta t. And soon you'll be doing these things in calculus if you haven't done it before. And this is what's called a derivative when you calculate a limit like that. And it's dx dt is the shorthand notation for this thing. And that would be the instantaneous velocity, which we usually just write as v, or we might write this as v sub x because it's in the x direction. And next week we're actually going to start doing two-dimensional motion, where we'll have both a v sub x and a v sub y. But for now, that's the direction that we'll be heading. The last problem, or the last page of problems, I'm going to save for tomorrow. It's a bit of a chase problem, and I think we've had a fairly big bite just with the material we've done so far.